So, welcome everyone. Let's assume it's 12:16 because it is, and let's just start. So anyone else coming later can just join in and see how they do. So today, let's first of all stop stealing tables. If you did, I don't know. So and if you haven't started yet, don't do so. Either way. Apart from that note, a few other aspects. Still the exam discussion. I really didn't push that too much. Any objections to doing the exam immediately after the end of the course? That would mean on the 14th to 12th to 14th of May this year, not next year. No? Yes? Sure. Objection? Or not? Sure? No. Just sweet? Okay. So I lock that in and see if anyone starts shouting sooner in the next few weeks, or days rather, because I want to fix that as soon as possible so we're kind of more comfortable with that. So that's number one. What was the other thing? Right. You have an assignment, right? Yes. Who started on the assignment? Okay, 3 people, 5 people, okay. Who finished it? Everyone who's not here, I suspect. All right, okay, one did finish. Cool, brilliant. Okay, so you can just come up, show us your demo.
No problem. What was that online site about Pac-Man again?
That's right. That's right. Yeah, let's say, I mean, Pac-Man per se is not super original. You may have caught us there, but at least we share the intuition of how it works. Right. So, all right. So, what did we talk about in Pac-Man? What didn't we talk about yet that you still need for Pac-Man? If you think about, how to get about doing things, what is one of the aspects that we didn't talk about yet? Reflect on Pac-Man. Did anyone look at the code that we gave you or resources? Yep.
The file with the levels.
The files with the levels, yep, that's number one. Good. Yep, good. Yeah, we probably leave you alone with this, so good luck. Yeah, we could talk about it. But there's another one which is probably more challenging. Which is that?
Rendering images on surfaces and geometry and parts of the image.
Yeah.
Like when we have the Pac-Man and Ghost Sprite, that's one big image, but we only need parts of it. Yeah,
that's right, that's right. So who of you inspected the files and looked at it? Yeah, the map is a valid point, but the scary bit is, yes, the scary bit should be the collection of individual Pac-Man positions and behavior and so on. So and those are referred to by sheets. So you have one that includes everything you need, hopefully, meaning Pac-Man and the ghosts. So how do you actually deal with this one? Or more importantly, what are those elements called? Those pictures, as you refer to them.
Sprites.
Yeah. Okay. And if we link them, yeah, we link them to.
So the pictures can have on your disk. You can have a lot of different formats like PNG, BMP,
yep.
JPEG.
Yeah.
But the idea is once you have loaded them into memory, they all are converted to the same format, which we call texture.
Mm-hmm. There you go. Yeah, that's the texture thing. Right. So, and what's the purpose? Well, texture. Okay. So why do we use concepts of textures in the first place? I mean, fundamentally, what are images made of?
Pixels.
Yeah, and pixels. How do we perceive pixels? What's
color?
Color mostly, right? So pixel assume we have a given coordinate and position, right? So the only other attribute that we carry is color, right? So we actually see pixels. So why do we need textures? I mean, if everything is basically every pixel is rendered as a or shown as a color, right? So a specific I don't know, RGB combination. So why do we still need pictures and textures?
Well, we started discussing
yep.
sort of loading them into the VBO in the same area,
yeah.
like in memory.
Okay.
So we started discussing the possibility of putting the data from the pictures you've given us into sort of that format, so loading or compiling the textures,
yeah.
well, the images
yeah.
into something,
yeah.
which apparently is textures.
Yep. Cool. That's textures. Where I want to get this. So can't we, in theory, now you got all the sprite sheets and all that magic, can't you? Isn't there? Couldn't you, in principle, model everything individually by specifying vertices along with colors and loading them into buffer objects? Wouldn't that be an alternative?
Yeah.
Yes. No. Yeah. Any reservations? Let's say a but.
Yeah. So when you have textures,
Yep.
you can sort of outsource it to maybe other programs which are better suited for creating this
Mhm.
kind of content.
Yeah.
It's not ideal to sit actually program how the game should look. It should be done in like Photoshop or Blender.
Cool. Yeah.
So you can, yeah.
That's
It's
Any
like a separation.
other?
Yeah.
Did everyone get what we're talking about? Yes, right? So the idea is basically, this is basically where the designer could possibly come in, right? So could you please give me all the vertex coordinates, including RGB specifications, so I can load it into my vertex buffer object? Cool, so that's provided by the designer, so the coder can just get the vertices. It's probably not happening in real life, right? So the usual designer probably uses specialist software, right? So actually create pictures, images, whatever else, and you kind of need to, well, use it in your code, right? So first of all, you literally have a better overview of the big picture, actually creating an image that you want to project into in your program. But what's another challenge that you are actually facing? So textures simplify the representation, the automatic mapping of color onto particular vertices. But what's the second aspect that we're dealing with in OpenGL in particular?
I'm not sure if this is what you mean, but selecting a sub-texture from the texture, like just selecting that this is the texture now, and then we move it a certain amount of pixels, you offset.
Exactly, right? So you need to do some sort of modification. We talked about transformations a bit, right? So what were some transformations we covered to some extent? What was the one you're just referring to? Yep.
Translation.
Yep, cool. Yep. Which other ones do we have? Scale and rotation, right? So those are the other two ones that we briefly dealt with. So that's the idea as well, right? So not only do we project the texture onto a coordinate system of our choice or our definition in a way, but also we want to have it manage all the possible transformations that we apply to our geometry, right? So if we, for example, rotate or scale or translate an object, then we want the texture to move along with this and retain that mapping, right? So what I want to get across here, the idea is that texture is basically just a massive simplification of the rendering process, because most of the heavy work will basically be outsourced to the GPU itself, right? So the GPU keeps track of the mapping between vertex and particular texture coordinate, and then can apply all the geometric transformations that you do to the texture as well at the same time. Yeah, so that's fundamentally the idea. So it's yep.
Also, there's other aspects where you can use the textures to pre-compute operations which you had to do in real time. You don't have to. You can do it before runtime.
Yeah.
To like bake it into the texture. For example, shadow and lighting reflections. You can save a lot of performance, gain a lot of performance.
Yeah, either way, I totally know what you mean. So yeah, that's right. You can do sophisticated pre-processing that is possibly not feasible in real time, or historically hasn't been possible at all on your graphics card in the first place. So you can just bake it into the texture itself, right? So that's a good point. Yes, it's actually very good. Right. So so obviously, just to the standard visualization that you find. We talk about this a bit more involved on Friday. I just want you guys get to intuition that's going far enough so we can actually start the lab or start dealing with textures and sprite sheets, because Ahmed prepared the lab in that respect, and you guys need to know that soon for your assignment, right? But I wouldn't want to wait until Friday to talk about it, so it's a bit tight otherwise. So the idea is as follows. We have some sort of geometric representation, right? So let's say, it's probably not a pyramid, but let's call it a pyramid. And then we have the texture, right? So the idea is that we identify which of the vertices, the coordinates, actually map to particular texture coordinates as well, right? So we deal with yet another coordinate system that you need to cover, right? Apart from the geometry here, we actually have another set of dimensions we now need to deal with, and conventionally referred to as V and U, right? So the two-dimensional texture coordinate system. Of course, textures can be three-dimensional as well, but we ignore that fact for a second, because in the end, our little Pac-Man program now is two-dimensional, and we can still perform all the transformations in order to map it onto a surface that we model in OpenGL using those 2D textures anyway. So that's fundamentally the idea. And if you do that, you're able to, you know, do all the transformations that you are actually just doing on your surface, and the textures will be fundamentally attached to the vertices that describe a particular triangle, right? So you link the vertices of a triangle to a texture coordinate, and from then on, basically, OpenGL does the rest for you, or your GPU rather does the rest for you, translates it, rotates it, and so on, stretches it, so it still retains the proportional representation on the surface that you are attaching it to. That's the fundamental idea. And the whole process involves a few basic steps that I will just briefly go through. So one of the aspects, we come back to that later, is that you obviously need to have a let's ignore that bit. So that we obviously need to initialize our VBO as usual. So we have our vertices vertex representations that we want to work on, surface, and our basically geometry we want to be dealing with. Then we also need to load the texture. And following this one, this is what we ignore right now. Then we need to link the vertices with the texture coordinates. So our coordinate system becomes a bit more, or vertex specification rather, becomes a bit more complex, because it's no longer just vertex, in this case two-dimensional plus color, but it's actually vertex, color, and the texture coordinate associated with this. Makes sense? So we're loading a texture. The texture has UV coordinates. Yeah.
Do you really need color anymore when you have the texture?
Yeah, that's right. So we could actually sacrifice that, yes. But let's stick to the complete specification for now, and then we can think about how we can actually compress space. That's possibly a pathway to go down in optimizing the code in our case. Do we deal with transparency? Not really, right? Not now, so yeah. We could, yes. But let's keep it complex. So for the sake of simplicity, keep it complex. No, in fact, it's most of the time you'll find it this way. So because we talked about having the vertex shader, the associated fragment shader, and now we link the coordinates as well. So basically now you have a vector that consists of, 1, 2, 3, 5, let's say 7 elements, right? Per vertex. And in addition to that one, I don't need to go back to that one. We just now need to, in contrast to the previous approach, we do no longer simply pass the entire set of vertices and draw them on the plane, but instead of that, we actually identify the elements or the specific vertices and their associated texture coordinates by index, and send those to the graphics card, to the GPU, to actually be rendered and displayed. And the reason for that is that textures are often well represented, let's say, as a rectangular, in some sort of rectangular format. That's probably not, is obviously not the only way of specifying them. But when we draw, we tend to use triangles by default, right? So it's our preferred way of rendering on in OpenGL, at least if we deal with surfaces, right? So, or what other alternatives do we have? We can have quad representations, but triangles is the default. So we need to be able to basically map the texture onto triangles. And for this reason, we actually need to identify, okay, which parts of the texture belong to which points of which triangle. Right, and that's done based on an index. So the injected triangles are just so elements of the code. You'll see that soon anyway on your own machine. If it compiles, we'll talk about this in a second. And here's the whole specification. So just to give you a clarification on this one, if we, well, let's backtrack a bit, what's actually happening in the background here. So first of all, the lab will load a sprite sheet, right? Sprite sheet contains all possible positions or movement positions of a character that is represented, so it's loaded. And the magic happens down here. That is basically x, y coordinate, so 0.5 and 1, 0.5 and 1. Then the RGB values right now, yes, which are conveniently white. And followed by the texture coordinate that is associated with the particular vertex, right? Basically the geometry in the display. So instead of sending this as one to the GPU using the GL draw arrays method, the idea is that now that those different vertices are indexed, and you decide which ones are to be plotted as or rendered as one particular triangle. So we see it, for example, that we have 4 vertices here. Good night. And then we just need to decide which of those 4 vertices belong to one particular triangle and which one belongs to the second one. So we have a new concept of elements that is introduced here. For example, the first triangle consists of the element 0, 1, and 2, so the first 3 elements, whereas the second triangle consists of element 2, 3, and 0, so links back basically. So this way we can represent the I think pretty much quadratic texture, or using triangles. That's the key idea here. So that's the concept. That's the only thing that's slightly different. You have an extended coordinate system here, or buffer representation, now including the texture coordinates, and you index those ones using elements specifications, and then you send it over using for rendering using a slightly different call. That's called GL draw elements. So we actually pass we link the elements along, and they basically are then used to actually render the proper vertices in order to do the mapping for us. So without going too much into detail further, because there's, I don't know, else we end up in a full-on textures lecture, I guess. We probably let you guys play around with this and explore that a bit more. I just wanted to give you those few pointers, else I had the impression that you may be totally lost as to what's happening in that lab, because the idea is fundamentally explore on your own, good luck. I think with this help you should be able to understand better how this mapping hopefully works and play around with this, particularly if you modify the elements. So what it means for you in this particular lab. So first of all, load the DAO, load the texture, we talked about this, do the linking, and then specify the elements, so the elements of the vertices that are to be rendered, call the GL draw elements. Some aspect you need to deal with possibly is controlling time, because the rendering is pretty much up to your rig. So it depends on the performance of your machine as to what you actually see. So you may need to introduce some sort of delays or sleep mechanisms that slow down your rendering process. And there's some other aspects that we'll talk about on Friday, but you can just leave them as they are in the lab right now, but they just describe how textures behave if they're increased in size or reduced in size. Remember, textures are basically fundamentally pictures, right? So they have a fixed resolution, so they're rasterized in this case. So the system, or OpenGL, needs to instruct the GPU somehow as to what needs to be done if the texture is increased in size, meaning the pixels are increasing in size. So what should be the possible behavior there, or what's the way of reducing pixels in size? So if you're, for example, zooming out, suddenly 4 pixels become 1 pixel, right? Because of the smaller representation. The screen size is fixed, but your object size may change. So an OpenGL can automate operations on that as well. But it's not something you need to play with. Cool. In terms of lab, the instructions should be as usual down here in the textures section. Ahmed did a good job in describing again the structure of this of the VBO layout, and we are using the soil library, right? So why did you pick the soil library?
Easy to compile at least. So there are other libraries as well, like Devo, and but they have a lot of dependencies. So this one is really good and easy to use, and it also it's very simple. It only it can render only the texture part directly to OpenGL. There are other libraries that have more functionalities, but I think for this lab this is a good way.
Yeah. So it's a good starting point. If you feel inclined to try out other stuff, go for it, right? So there's usually a bit of that concern that as we, if you travel nowadays, the first thing you go and look for is probably something like TripAdvisor or Wikitravel to figure out what you should do and shouldn't do. And the same is for libraries, right? The first thing you want to do is not just appreciate the beauty and the feature set of a library, just check what happens in the forums, right? So how many people don't get their stuff done because there's an obscure bug in libraries. So, and that is basically the principle of choice here. So having a simple library, simple functionality, hopefully even readable, if anyone wants to inspect the source. But that's a reason of choice here. But if you find some other library you want to explore and play around with, eventually go for it. The same for the assignment, right? So whatever you want to do, as long as you satisfy the requirements of getting some Pac-Man style figure going there, the mechanics underneath, apart from stealing other person's code, is pretty much up to you, right? So you can be reasonably creative there when it comes to that. So yeah, so that's the basic idea, just getting something going. Because I think this lab is a good starting point for you to think about, okay, how to actually address and use the textures that we provided as part of Pac-Man. Good. Any, no, there's nothing else I need to mention. Yeah, some tasks here. Another note. So last Friday it was. Yeah, it's 1 weekend ago, so it's a bit blurry already. Last Friday we had a lecture on C++ and U, quite literally. And I think you guys took, or the ones that attended, took quite a bit out of it. So in response to that one, obviously, we're equally learning as you are doing. So if you find bugs or issues in our labs or code that we provide, send pull requests, right? So we need to fix our work as well. And you are equally responsible in contributing to the course and the quality. So you are held responsible for finding and fixing our bugs in our code. So if you have suggestions for improvement, go for it, right? Everything is on GitLab, so you're invited to actively contribute there as well. Questions? Did I forget anything? There's a question, of course.
In the lab code.
There you go. That didn't last long.
I'm just curious about, of course, there are two textures. You load two textures, and
you can
from
also,
the one.
Yeah, you can. Yeah, the idea was like if you want to use multiple textures, you can just easily load like that and keep the handle. That's it.
It's just an example.
It's just an example. So if you want to make two of them display at the same time, you can just use the other one.
That's right. What
takes,
Jonas was referring to is the fact that this one is replicated down here.
Yeah, apart from it being an example, is there any use of loading the same picture?
You can load different pictures, and actually there are different functionalities in which you can mix, like two images. There are a lot of things you can do.
Yeah.
So it's one of those. Basically, the labs are the tutorial ish as well. So so you can just extrapolate and think, okay, how if I want to use yet another file sheet, how could I do it? Here's a partial answer, even though it's not actually used in that. Any other thoughts? By the way, did anyone compile and run the lab, particularly Linux people?
Yeah.
Yeah, works. When did you do it? Just now?
It's just a white screen with black rectangle at the.
No, it should be this guy.
Okay.
So
it's not that guy.
It's not that guy. Oops.
But
when did you pull that up? Just now doing that?
Yeah, 5 minutes.
Okay. Because we did some last-minute modifications, so we may need to debug it. The Windows people will be fine, as usual. But the Unix/Mac world is, will suffer as usual. But please let us know, so we'll fix it up as well. OpenGL should be at 4.1, so that shouldn't be an issue. for Mac people. Any other questions? Else, just happy hacking, and we go from there. Good, cool. More details on Friday. So I'll switch off the stream now. So because basically now it's just local work here. Thank you.